Okay, so in the last lecture, what we did was that we tried to understand how magnetic boundary conditions work and how we can compare the magnetic boundary conditions with electric boundary conditions, and the result that the expressions that we derived were by the comparison of these two different magnetic and electric fields, and we saw that the rules in magnetic boundary conditions are basically reversed. So, reflecting on that, there were two magnetic boundary conditions that we derived in the last lecture. The first one was that the normal components of magnetic flux are equal, just like the tangential components of electric fields, electric flux density were equal in the last electric boundary conditions topic. And similarly, the second boundary condition that we derived for magnetostatics was that H2T minus H1T is equals to Js. And for this type of equation, we said that wherever the current density on the surface of the boundary is zero, the tangential component of magnetic field intensity is also going to be equal, just like the normal components. But obviously, that is a special case scenario. And now the thing that was left in the last lecture because of time shortage was another form in which these boundary conditions were mentioned in the book, and that might confuse you a little bit. They basically, what they did basically was they tried to mention this boundary condition in the form of vectors, and the expression that is written in the book is n2 hat cross h1 vector minus h2 vector that is equals to js. So what he did basically was that he jumped straight to this equation after this. So this might confuse you a little bit. So I thought that in order for you to understand how we reach to this equation, from this equation we need to specify things a little bit so that you may be able to understand it a little better. So how do we do that? First of all, we are starting with this equation. So we have H2T minus H1T, and this is equals to Js. Now if we want to write this equation in the form of vector, first of all we need to reflect back to how these vectors were identified. So we'll draw that boundary once again here, and we'll see that the medium 2 was here and medium 1 was here. This one had the permeability of mu2, and this had the permeability of mu1. And obviously if this is the second medium, then the normal vector of this second medium will be normal to this boundary. So n2 hat will be mentioned like this, and in medium 1 we had h1 and medium 2 we had h2. So these are the two vector quantities. Now if we want to mention this was the h1t and this was h1n, similarly this was h2n and this one was h2t. Now if we want to mention this tangential component in the form of cross products, then we know that the tangential component is going to be the what we'll call it, this is going to be the sign component of this h2 vector. Or if we can draw this once again, we can say that if this is n2, this is n2 hat, and this is h1 obviously, then we have this angle right here, and this is the tangential component. So this side is basically, because this side is opposite to theta, so this side is going to be n2 h1 sine theta. Okay, so the magnitude of n2 is going to be 1, so we can ignore this, and this is h1 sine theta, and this is basically what, ht. So this means that if we want to write this h1t or h2t in the form of uh, cross products, then in the form of vectors, in the form of cross product of vectors, then we need to take the cross product of these two vectors such that the fingers will curl from h1 towards h2. So we can write this as h2 vector cross n2 hat. This basically is equals to h2t. Similarly, for h1t we can write it as h1 vector cross n2 hat, and this is going to be equal to js. Okay, so now we can take n2 hat common, and then we can write h2 minus h1 cross n2 hat, and this is going to be equal to js. Now we know that this is a cross product, and if we want to change its arrangement, then obviously there will be a negative sign. So if we write it as n2 hat cross h2 minus h1, then we will have a negative sign here. This negative sign will go into these brackets, and as a result we'll have n2 hat h1 vector minus h2 vector, and this is equals to js vector. So this is basically the equation that he has written at the end of this topic. So I thought that maybe you will get confused by taking a look at this equation and then this at this equation, and you'll see that here you have h1 first, and there you had h2t first, and how this came to be. So I thought of explaining it a little bit for you people. So this was related to the last lecture. Now we'll move on towards the topic for our today's lecture, which is inductance. So the topic for today's lecture is inductance. Now, as we said earlier, that everything that we study in electrostatics, we have a counterpart of that terminology in magnetostatics too. So the inductance basically is the magnetic analog of electrical capacitor. It has a counterpart in electrostatics, which is known as the capacitance. So we studied capacitance in electrostatic, and now we're going to study inductance in magnetostatics. What is happening here is that just as a capacitor can store electrical energy in the electrical field, in the form of electrical field which is present in between the medium that is present, or a dielectric that is present between two conducting bodies, we have electrical energy which is stored as a by means of electric field which is present inside that dielectric material. That is the same case which is going to apply here, and in this case the inductor will be storing its energy in the form of magnetic energy, and it will be stored in the volume comprising the inductor. Okay, so in order to understand this thing a little bit, we'll take a typical example of a solenoid. So in a solenoid, what happens is that we have a closely wound coil, and we call it a solenoid. We'll try to draw it like this. So this is basically a solenoid. I think I should draw it a little bit more wider so that you may be able to understand what is happening. So this is a solenoid. Okay, so inside this solenoid there is whatever there is in between these turns, this is called core. So it can be it can contain free air or a free space as a core, or we can fill this internal thing of this solenoid with a ferromagnetic material or any kind of magnetic material for that matter, if we want to increase the permeability. Now the purpose of mentioning this solenoid here is that if the wire has n number of turns and a current of I magnitude is flowing through solenoid, then the solenoid can produce uniform magnetic field within its central region. The only thing that we need to be careful about is that these turns should be very closely bound so that the leakage, the flux, or the number of lines that can leak from the space in between the turns that is minimized. So if these turns are very closely wound and a current I is flowing from this solenoid and it has a number of turns n, then as a result it has the tendency to produce uniform magnetic field within its central region, and that uniform magnetic field will resemble to that of a permanent magnet. So we have studied this phenomena already. So he's saying that we'll have a uniform magnetic field in its central region. I'm sorry, I can't draw it uh, very neatly. So we'll have these kind of magnetic lines of force, and we'll say that these magnetic lines of force will be similar to what we saw in a permanent magnet. So if we'll see that inside these lines, inside this solenoid will have a pretty uniform set of magnetic field lines. So we can say that now it can uh, depict or it can act or it can behave like a permanent magnet. So this is how a solenoid looks like. So what we'll do here is that we'll try to calculate the magnetic field inside a solenoid. So magnetic field inside a solenoid is the topic, and for that our goal is to drive an expression of magnetic field, magnetic flux density B for interior region of solenoid, which has n number of turns per unit length. So small n is basically number of turns per unit length. Okay, so in order to drive the goal, and we'll mention the goal here, the goal is to drive the expression for B inside solenoid, the central region of this solenoid. Okay, so we'll treat the turns as circular loop, as we already have mentioned that these circular or these loops have to be very closely wound. So if they are closely wound, then they will be like a circle. So we'll treat these turns as a circular loops, and this solenoid will have the length. We can represent the length of the solenoid by small l, and we'll represent the radius of this solenoid by a, and the current flowing through this solenoid by I, in order to perform our analysis. So let's start by taking a magnetic flux density at a single point P, which is located on the axis of the solenoid. So in order to do that, what we'll have to do is that we'll have to redraw this expression in such a way that we can perform our analysis on this thing. So let's try to do that. What we'll do is that we'll draw a, I'll try to draw this as straight as possible. We'll draw a axis, an axis. So this is an axis, and this should be the other axis. So this is x and this is z. And what we're doing is that we are taking a look at this solenoid just like we are looking at our screen right now. So we're looking towards the screen, and we are trying to depict the direction of flow of current. So these circles are showing the turns. Uh, these are the second part of that turn. Okay, so what he's saying is that the current is getting out of the screen from this. So we'll represent them by mentioning a dot, 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 and they're going into the screen. So here is the cross. The circles are too small, so you might not be able to see the crosses, but you know these are crosses. So the current is going into the screen from this loop. So I think you can understand that we have uh, drawn this solenoid here. We just have eliminated these lines. So we've shown the direction of current by means of crosses and dots. So he's saying that what we are doing is that we are trying to find the magnitude of B at this point, which is at the axis of this solenoid. So if this is the direction of current, and what you'll do is that you'll try to figure out the direction of B. So what will be the direction of B? You will curl your fingers from in the direction of current, and your thumb will point towards the direction of B. So if you take your right hand and you curl your fingers in the direction of current, this is coming out of the screen and this is going into the screen. You curl your fingers, you'll see that your thumb is pointing towards these directions. So as a result, we'll say that this is basically the direction of B. Okay, it is in the Z's direction. Now what we have to do is that we have to find out the value of B at this point. But at this point, the value of B is not due to a single turn, but it is the value of B at this point will be a sum of all these turns, the contribution of all these turns, the contribution of the current flowing through all these turns. So we'll have to take all of these turns into account. For that, first of all, what we'll do here is that we'll try to write the expression for a single circular loop, and the expression that we derived was h is equals to z hat I dash a square divided by 2 a square plus z square and raised to power 3 by 2. We derived this expression in example 3-4, and this is the same example that you inquired me about, or I said that we'll discuss about this example, that what will be the direction of magnetic field intensity above the circular loop or below the circular loop. So this basically corresponds to that example. So this was the equation for the point at which we wanted to find out the value of magnetic field due to a single circular loop. But now there are certain modifications in the scenario. We have different number of turns, and we can't just take this value and we can use this expression to find out the value of P at this point, because we have a lot of circular loops in this scenario. So we'll have to modify it accordingly. What we'll try to do here is that we'll try to take an elemental length, and then we'll convert or we'll integrate that expression for the whole length of the solenoid. So first of all, what we'll do is that we'll take an incremental length. We'll say that this and this, the length in between these two uh, number of turns, which is basically dz. This is the incremental length that we are taking in order to apply our analysis. So this is the one r, and this is the second r. So the angle between these two is going to be d theta, and the angle from this is going to be d theta. Sorry, this is going to be theta. So now what he's doing is that he wants to modify this equation according to this scenario. And if we're taking an elemental length, then this means that this current was the current that was flowing through a singular loop, but in this incremental length there can be a number of loops. So we'll change this expression of I dash into an expression which takes into account all the number of loops that are carrying the current in this incremental length. So if this is the length and n is the number of turns per unit length, then we can multiply the number of turns per unit length with the length. Actually the length that we are considering will get the total number of turns, and then we'll multiply the total number of turns with the amount of current that is flowing through each turn. So if I was the amount of current that was flowing through one turn, and we want to calculate the value of current which is flowing through total number of turns that are in the in this incremental length, then this means that we want to calculate ni, and for n, the total number of n, we needed to know what is the number of turns per unit length and what is the length that we are considering. So n into dz, this is going to be equal to a capital N, and I is going to be the current which is flowing through a single turn. So this is basically the expression for I hat in this case. So in this case, the expression of I hat will be I, N, and dz. dz is total length that we are considering. Small n is total number of turns per unit length. We multiply these two things, we'll get total number of turns, and then we'll multiply that total number of turns with the amount of current that is flowing through each turn, and we'll get the total amount of current for this thing. So we have the value of I hat here. What we'll do is we'll try to put the value of I hat in this equation, and we know that we are taking an elemental length. So as a result, the amount of magnetic field intensity that we'll find out will be is going to be dH, not the whole magnetic field intensity. So dH is now going to be z hat and I n dz divided by 2 a square and then z square and then 3 over 2. So now we have converted this equation, or we have modified this equation for this specific scenario. There is another thing that we need to take into account. This we forgot this a square, so this a square is also here. There is another thing that we need to take care of, is that we need to calculate, or we need to integrate this expression for this whole surface. It means that we need to take into account, let's draw, if we want to integrate this expression for this whole surface, for this whole solenoid, for this whole thing, then we'll need to take the integral from, this is the last extreme point here, and this is the starting extreme point here. So if we say that this is theta 1 and this is theta 2, which is the other extreme point, then we can see that we have to integrate, if we want to take into account the magnetic field intensity at this point due to all these number of turns, then we'll have to integrate this equation for from theta 1 towards theta 2, so that we can take in, or take the sum of the contribution of all the number of turns that are inside this solenoid. So in order to do that, we'll have to change the expression in the form of theta, so that we can integrate this equation in the form of this integration. We can integrate this expression for the whole solenoid. We can't just integrate it according to dz. So this means that we'll have to convert z's perspective into theta's perspective. So this was the first thing, this triangle that we took, theta and this. So if this is the triangle, then this is going to be z and this is going to be r. So if we want to convert the z in the form of theta, then we'll take tan theta is going to be z over a. Okay, so perpendicular over base. From here we can write that z is equals to a tan theta. Now we can use this, because now we have converted this length in the form of theta and in the form of radius. So now it is in the form of what we'll say about this, it is in the rectangular coordinate, or cylindrical coordinate system. So z here is a tan theta. What else do we need to mention in this equation in the form of theta? Uh, we'll need to transform dz too. So we'll take the differential on both sides. We can say that this is a So the tan theta is the derivative of tan theta is secant square theta and then d theta. So we have dz. Apart from that, we have z square. So z square is going to be a square tan square theta. I think now we have transformed everything which was mentioned in the form of z in theta's perspective. So now we'll rewrite this equation by putting in these values. If we rewrite this equation by putting in these values, we'll write it as b is equals to mu naught, sorry, mu, obviously we're not talking about free space, mu h, and we'll add another thing which is mu in this equation. So this is going to be z hat mu n I a square, that was already there, divided by 2, then integration, and then we have a secant square theta, that is in the place of dz, divided by, we had a square plus tan square theta. So let's use this first. A square plus a square tan square theta, sorry, what we're doing here is that we're putting the value of z. So a square plus a square tan square theta, if we take a square constant or common, then we have 1 plus tan square theta, and we know that we can write it as secant square theta. So below, in the denominator, we can write this as a square secant square theta, and then we have 3 by 2. So this 2 is going to be cancelled and this 3 will come inside, and we'll rewrite it as b is equals to z hat mu n I a square divided by 2, and then here we have uh, a secant square theta divided by a cube secant cube theta, and then we'll have d theta, and then this a and these a square, this is going to be cancelled with this, squares is going to be cancelled with this, we'll have 1 over secant square theta. That is basically the reciprocal of sine cos, and we'll integrate this from t1 to theta 1 to theta 2. Okay, I think we'll have to use another page, or we'll just remove this. So we'll remove this, and now what we have is that we'll solve this integral. B is equals to z hat mu n I over 2, and inside this will have sine theta 2 minus sine theta 1. So let's go to another whiteboard. We have B is equals to z hat mu n I divided by 2 sine theta 2 minus sine theta 1. So the thing that remained while we were in the integral was cos, and then we took the integral and we put in the value of theta 2 and theta 1 inside this equation. Now once again he's saying that if the length of the solenoid is way too large, let's go back. He's saying that, just a second. He's saying that if the length of this solenoid is way too large and we are at the center of this solenoid, then obviously if this is going upwards and upwards and upwards and upwards and upwards, then as a result this theta 2 will most probably be approximately equals to 90 degree, and similarly for theta 1, the theta 1 is going to be approximately equals to minus 90 degrees. So he's saying that if we put in these values by saying that our by saying that the theta 1 is approximately equals to minus 90 degrees and theta 2 is approximately equals to plus 90 degrees, and we put in the values here. Then he's saying that we'll have the value of b to be z hat mu n I, because 1 plus 1, this is going to be 2, and this will cancel each other out. And here n is basically the number of turns per unit length. So if we want to mention it in the form of capital N, we'll say that as b is equals to z hat mu capital N over L and then into I. So we have talked about it earlier that capital N is equals to small n into L, because this is total number of turns and this small n was number of turns per unit length. If we multiply number of turns per unit length with length itself, we'll have total number of turns. So we usually have total number of turns given to us by the author or by the examiner. So that is why we try to mention this equation in the form of capital N instead of small n, so that you might not get confused about which n is going, which n is do you which n do you have to use in the solution of your numerical. So he is also saying that even though this expression is derived for midpoint of a solenoid, we have derived this expression for midpoint of a solenoid, but it is valid for approximately all the points inside the solenoid. Why it is valid for approximately all points inside the solenoid? Because we already have talked about this. Like we said that inside the solenoid, the and the magnetic field is going to be uniform. And what is the meaning of uniform? We have talked about it so many times. The meaning of uniform is that it is constant at all the points. So this means that this expression is not only valid for the midpoint inside the solenoid, but it is also equally valid for all the points that are inside the solenoid except at the sides or away from the sides, outside the solenoid, that we can say. So he's saying that this expression is basically valid for all those points. So this was our goal of this topic. He's also saying that magnetic flux, we know that we passed a current through a solenoid, and as a result a magnetic flux was generated. And that magnetic flux, if that magnetic flux is linked with an other thing, with an other conductor that is placed in its vicinity, and this magnetic flux is changing its value, then as a result this will have an effect of generating an EMF in that conductor according to Faraday's law. But he's also saying that the magnetic flux of a coil does not only link with the an other coil, but it also links with itself. So the linkage of the magnetic flux of a coil with itself is called self inductance. So magnetic flux linkage in a circuit due to the magnetic field generated by a current flowing in another circuit, that is called mutual inductance. So he's saying that there are two types of inductances. The first one is the magnetic flux linkages of a coil with itself, and the other type of that inductance is the magnetic flux linkage due to passage of a current through a coil in another circuit, that is the mutual induction, because in that case we have two different coils, and the magnetic field that is linking with the first coil is due to is generated due to the presence of current in the second coil. So that is mutual inductance, and the first one is self inductance. So the other thing that you need to remember is that whenever we talk about inductance, that means that we are talking about self inductance. We are not talking about mutual inductance unless we are specifying it specifically. We are saying it explicitly that we're talking about mutual inductance. If there is the term inductance, then you have to assume that he is talking about self inductance. If he ever talks about mutual inductance, he will mention mutual before inductance, explicitly. So you need to understand and you need to remember that thing. So this is it for today. If you have any questions, or if you are ambiguous about anything that we have studied in this lecture, feel free to ask all your queries in the interactive session. Thank you so much.